Hello everyone, this video will talk about a titration question. Okay, so then you go, how do you know it's a titration, right? First thing first, we recognize it quickly. We have an obvious hint from the question saying titrated, okay? And then we also know, okay, then the question will be, oh, what type of titration or excuse me, or looking into, is it strong in terms of strong acid, strong base, or weak acid, strong base, or the other way around, a weak base with strong acid. Okay, so then let's read into it. Okay, so then from the question we recognize, okay, we have an acidic acid. Okay, so then you go, oh, that's not one of my strong, so it's weak, but I don't know what the chemical formula will be, but then we always can just write out, right, its generic form, HA, representing a weak acid. Okay, so then we'll have a weak acid titrated with what? Sodium hydroxide. That's a strong base. Okay, so you go, okay, I have a weak acid, strong base titration, and as always, I'll suggest us, right, to try to draw out, okay, so what's happening over here, so give us a good idea, right? Okay, so then just say our setup, right? Okay, so inside this Elmer flask, okay, so we'll have this 25 ml of a 0.50 molar of this weak acid, and then in the burette I have my strong base. Okay, so the strong base right over here we're given with a concentration. Okay, so then you go, oh, how much of this weak base I'm adding to my LMR flask and having the titration? Then you go, it's not given, but let's keep on reading and see from where else we could possibly figure that out. Okay, so then the question is asking us, what's the pH at equivalence point? Okay, so then you go, okay, this question is specifically talking about at equivalence point. Okay, so it's already telling you it's at equivalence point, which is telling us a very important information. Okay, so at equivalence point, we should know what it means. Equivalent, right? Okay, equivalent. What's equivalent, right? Okay, so it's at equivalence point, then most of the acid equals to most of the base, okay, stoichiometrically. So which means at equivalence point, all of your acid and base, right, the two chemicals that are titrating with each other, they're gonna be completely reactive with each other stoichiometrically, so you will have none of the acid base left. Okay, so that's also why most of the acid will equal to most of the base. Then, right, the question will be, what we'll have, right? Okay, if they are completely reacted, but then what's gonna be here, right? Okay, inside the LMR flask. So that will be the question. Then you go, right, what's gonna be there? Then that will be, let's see what if they react, right? Or what happens, right? Okay, so then let's see when we have this weak acid reacting AQ, that's aqueous solution. Okay, reacting with strong base sodium hydroxide. So where the product will have this NaA, right, salt and water, because we know we have an acid-base neutralization reaction. Okay, so then after reaction, as we recognize, all of the acid and base will be completely reacted with each other, okay, in terms of stoichiometrically. Okay, and then what do we really have? We'll have the products. Okay, so at equivalence point, you have salt and water. So then over here at equivalence point, you have a salt solution. Okay, so then our job is actually calculating pH of the salt solution. Okay, so now again, of course, following up, we need to analyze how that salt behave. But before we get to that point, we also would need to know, right? Okay, so how much is left in terms of moles? Okay, so then from that point, then we'll continue. Okay, so then let's try to figure out how many moles of this salt will be produced from this given information. Okay, so since we need to track out moles, okay, so then we're given info with what? Volume and concentration of that weak acid. Definitely we can calculate most of that acid itself. Okay, so then let's do that job. Okay, so most of the acid, I'm gonna just use the color. I use this color. Okay, so most of this weak acid, then that'll be volume times concentration. Okay, and of course you can convert that to, right, the proper units in terms of, right, we know molarity is, let's take express what it means, right, mole per liter. Okay, so that now all cancels out. Okay, so we'll have moles. Okay, this number came out as 0.00375 moles of that weak acid, as we already know, right? This is a condition. We know it's at equivalence point, most of acid equals to most of base. So this will be at equivalence point, we'll need the same number moles of the strong base. Okay, so which also gonna be 0.00375, right? That's because right over here, that's what equivalence point means. Okay, so once we know that many moles of the base we need, and we also have the concentration, then from those two info, we could calculate what's the volume, right? Remember earlier we were wondering, oh, how much of this strong base we needed to add it into the LMR flask to reach equivalence point, and now from here we could calculate, okay, so the volume sodium hydroxide needed to reach equivalence point, that will be, since we need 0.00375 moles of that strong base, and then we have its concentration, again, molarity is just mole per liter. Normally, we do want the units in milliliters, so then I can do that conversion. After I do this calculation, the volume needed to reach equivalence point, that will be 25 ml, okay? So then you go, oh, look at that. We added 25. It's 25. Is it always equal? Is it always a 25? No, they're only equal to each other. Only reason is because we are using the same concentration of acid and the base. Okay, so then that's the reason. But the proper work is what we have just done. We need to figure out how many moles of the base we needed with the given info. That concentration will be able to calculate. Okay, so this is just the situation, right? We figure out, okay, now we need to put 25 ml of the strong base inside here to reach the equivalence point. Okay, so now of course the stoichiometry calculation should be quite straightforward because, okay, so what we start off with, we can call it as before, reacted, that according to stoichiometry coefficient, and then what's after. Okay, before just in inventory, what we start off with. Okay, so we start off 0.00375 moles. We know in order to reach the equivalence point, that's how many moles of the strong base we're gonna add to start off with. We have none of that salt and then water, right? It's okay, we don't really need to consider about water in terms of pH, right? Okay, so then now reacted, since they're gonna right, it's equivalence point, so they will perfectly react with each other. Now of course the number wise also shows us the same information, so then I have 0.00375 moles of the salt. Okay, so then at equivalence point, you have again all of the acid and base perfectly reacted with each other. Again, at this point we will, in this early flask, you just have that many moles of this salt. Okay, so as we said, right now the question will be, we're calculating pH of the salt solution. Then the question will be how the salt will affect the pH of our solution. Okay, so then what kind of salt we have? We should analyze that real quick. Okay, so again, as a aqueous, right, soluble salt, we know it's a strong electrolyte, 100% dissociating into ions. So we dissociate into sodium ion and this A minus. Okay, so these two ions, sodium ion is a counter ion of a strong base, so it's pH neutral. So which means we don't need to concern about that. So really the species will affect the pH of a solution is A minus, and his acetate ion. Okay, so itself is what? Is the conjugate base of our weak acid. Okay, so its identity is a base. Okay, so then how does base behave in aqueous solution? So then let's try to analyze that. Okay, so AQ plus water. Okay, so since it's weak, it's gonna reach equilibrium. Okay, so then since it's a base, what does base do, or how does base behave? Base will accept the proton, become HA, and then water in this direction behave as acid. What does acid do? Donate a proton, so end up with hydroxide ion. Okay, so then you go, oh, I am expressing a base, I have OH, that sounds all right, and then since I'm expressing its equilibrium, this is going to be KB, right? All of this, all the sign, right, they're consistent, all the information, that's all good. Okay, so then since now we're tracking equilibrium, and then we're gonna how the behavior is, right? So then we're gonna use S table. S table is based on molarity. Okay, so what's this concentration of this conjugate base? Oh, this 0.00375. But remember, that's moles. We need concentration. Then you go, oh, that's easy. We could totally calculate concentration. Okay, so concentration will equals to moles 0.00375 divided by liter, which is volume. Let's see, at this point, what's the total volume? This is also always very important for us to notice. Okay, you go, oh, I have a number 25 from the question. That's it. Now, that's also why we start off from calculating how much of the base you needed to add right into the solution. So it's total of the acid and base, the volume of both. So it's 25 plus 25. Okay, so it's going to be 25 plus 25. Since we know concentration is mole per liter, so we need to do this conversion. So that's 1,000 ml 1 liter, so be able to calculate the concentration. So then that's gonna be 0.075 molar. Okay, so now we got the concentration, and then there's a concentration of this conjugate base, so we're gonna put in 0.075. And this water is not going to affect our equilibrium initially. Before this happens, we have none of the products. Okay, so then we'll have minus x, positive x, positive x. At equilibrium, you'll have 0.075 minus x, x, x. Okay, all this information we needed to express our KB. Okay, so KB will equals to product over reactants 0.075 minus x, and what this KB value equals to? You go, let's see. The question give us a value but is that KB? No, it's Ka for the acetic acid, right? Okay, so, but we want to know the Kb of the acetic ion, which is the conjugate base of this weak acid. Then go, don't worry, I totally know how to calculate that, right? Okay, so Kb simply should equals to Kw divided by Ka. Okay, so then let's do that calculation. Again, Kw value we know is 1 times 10 to the negative 14, and Ka value is given from the question as 4.50 times 10 to the power of negative 4. So do the calculation. So on the left side I have x squared, 0.075 minus x equals to, over here we got 2.22 times 10 to the power of negative 11. Okay, so then you go, oh, now what, right? Now, small approximation, right? Okay, so we small approximate that value into 0, so then cross multiply square root, we'll be able to solve this x, so equals to 1.29 times 10 to the power negative 6. Okay, so then again, do not just automatically continue, oh, negative log this and that. Let's see what this x equals to. The x we solve is the hydroxide ion concentration. So then we can calculate pH at this point equals to negative log. We could then start from pOH since we have hydroxide, right? Negative log of hydroxide. Okay, plug all this value in, we'll get pOH equals to 5.89, and then we need pH. pH can be calculated by using 14 minus pOH will be 14 minus 5.89 equals to 8.11. Okay, so then that's the answer for this question. Okay, again, we need to recognize, right? So the whole idea is you need to see what type of titration you have. Is it strong, weak, right? Okay, so then once you recognize that for this question, it's already telling you equivalence point. Then again, bottom line, you should know equivalence point. We're really calculating. We're calculating pH of a salt solution. Then in order to calculate pH of a salt solution, you should know how it behaves by writing out this equation. Okay, and then also a very important part is knowing how to calculate the concentration of that conjugate base equivalence point. Okay, so then even before we get to the answer, remember you are calculating a salt, which is a basic salt. So then before we finish, you should anticipate, right? The answer should be above 7. Okay, so if you make mistake in the middle, that from knowledge that you know, that should be serving as a checkpoint. So then you go, oh, even though you thought, oh, I should have stopped at 5.89, but no, right? It's not, because you know you have a basic salt. Then you will realize, oh, where it went wrong. Then you can fix your mistake. Okay, so anyway, so this is titration question, and hopefully this is helpful, and thank you for listening.